We have some A-level questions here on reaction kinetics. And the first one goes, the oxidation of nitrogen 2 oxide is shown in the equation. Your nitrogen 2 oxide with oxygen reacting to give nitrogen dioxide. Now, the initial rate of this reaction is measured. Here is your initial rates as well as the concentrations of your two reactants from your respective experiments, 1 right up to 4. Roman 1 says, use the data in the table to determine the order with respect to each reactant. Show your reason. Now, you have to determine the order of the respective reactants. You know that your order of a reaction is the power to which the concentration of a particular reactant is raised to in your rate equation. For example, you have your rate equation here, which equals your rate constant multiplies your concentration of a reactant, say A raised to the power X. Now, this X is known as your order. That's your order. The power to which the concentration of a particular reactant is raised to in your rate equation. Now, looking at experiment 1 and 2, you see that this is constant, right? So the concentration of what? Your nitrogen 2 oxide is constant. So we can use 1 and 2 to get the order of your reactant oxygen. And look at it when it doubles. So it doubles. When it doubles, what happens to the rate? The rate also doubles, telling you that that is what for nitrogen or oxygen, sorry, it is first order. So you write it down using experiment 1 and 2. Oh, the concentration of oxygen is first order. The concentration of oxygen is first order because when the concentration of oxygen doubles, the rate also doubles. Rate also doubles. So you can say times 2. So also multiplies it multiplies 2, okay? The value multiplies 2. So you can check that out. Check it out, and you find it's just what 8.15 divides 4.08 gives you approximately 2. So now moving to your nitrogen 2 oxide, let me change my pen. I'll go to this color. So for nitrogen 2 oxide, I will look for where the concentration of your oxygen is constant, and behold, you have it here on experiment 2 and 3. So when it's constant, I would use this. Now, what happens here? This also doubles, right? So it doubles. The concentration of your nitrogen 2 oxide doubles. And what would happen with your initial rates? You see when you divide 3.28 times 10 raised to the power -2, take note, by this divides this, it's gonna give you 4. Okay, so we say it quadruples. It quadruples. So that's what happens. And when it quadruples, then that's the second order. This is a cube, please. So that's the second order. So using experiment 2 and 3, the concentration of nitrogen 2 oxide is second order. Okay, the reactant nitrogen 2 oxide, you can see reactant nitrogen 2 oxide is second order. This is second order because when the concentration of nitrogen 2 oxide doubles, what happens with the rates? the rate, the initial rate quadruples. Quadruples, that multiplies 4. Mathematically, you'd see the, or let me put it this way, you see you have 0.064 divide 0.032. That gives you 2, and she raised to the power something x, right? Which is what? 4. This 4 here. Remember, 3.28 multiplies 10 raised to the negative 2 divides 8.15 times 10 raised to the negative 3 should give you 4, and that is what? 2 raised to the power 2 using the laws of indices. So that's your x equals to 2. So the order is 2, or your second order. Yeah. You could also use some mathematics on your experiment 1 and 2 to get that for oxygen. So that is I hope this question doesn't pose any worry. And if you have any other way to solve this question, please, you can keep us a comment below, okay? Let's move to the Roman 2 part, which says calculate the initial rate in experiment 4. Now, you're gonna calculate this. We're going to look at this. And which pen can I use? Should I go back to my blue? No, let me go to brown. So before we start, I want you to note that we could use 2 methods to solve this. 2 methods. So method 1. Method 1, we could use the data. We could use a table to solve this question, all right? So we could use experiment 1 and 4. Okay. So using experiment 1 and 4, for example, you would find that the concentration of what? Nitrogen monoxide from 0.096 to 0.032 should give you, if you divide that, you have 3, right? So you would have 3, and that order should be 2, right? It multiplies. What about the concentration of oxygen 1 and 3? 0.036 divided 0.012. So if I'm using this, so that will be triples, right? And so I can call this my R4. Yep, I can call that my R4. So it triples. And what about it? This also triples, right? It also triples. So it triples here. 0.036 divided 0.012, it triples. So multiplies 3 raised to the power 1. Remember, the order for the reactant oxygen is 1, and the order for the reactant nitrogen 2 oxide is 2. That's why we're using 2 multiplies 1. And we are following the same principle here, right? Gives you what? Gives you, let's say, R4 divides 4.08 times 10 to the minus 3. So telling you that R4 equals 27 multiplies 4.08 multiplies 10 to the minus 3. And that should give you, I think, if you use a calculator, that should give you 0. See, so multiplies 4.08. So that should give you 0.11. Check, please. 0.11. Okay. 11 is not well written. So that is that concerning that question. And before we go to method 2, I want us to go to Roman 3 first. Yeah. So that is that about this rate. So let me know your feedback about this question, please. This particular Roman 2. Now we go to Roman 3. It says, write the rate equation for this reaction. So, of course, you could have it here. So your rate equation will look like this. But remember, we have two reactants. I want to change my pen, please. So what pen can I use here? Let me go to this. Yeah. So your rate would be your rate constant K multiplies the concentration of nitrogen monoxide, and the other was 2, right? And concentration of oxygen, you have that. So that's a rate equation. And Roman 4 says use the results of experiment 1 to calculate the K for this reaction, includes the units of K. Okay. So you could just go directly to make K the subject. Your rate constant, capital K, equals, or is it small k? Equals your rate divides square oxygen. And that gives you, we go to experiment 1. What are the reactants? The rate there will be 4.08 times 10 to the negative 3. You have 0.032 and 0.012. So you have 4.08 10 to the negative 3 divides 0.032 square multiplies 0.012. You can check that out. And when the units are concerned, you would have just put moles. I'll go to yellow. For my yellow, let me solve let me solve this first. All right. So you have 4.8, 4.08, sorry, multiplies 10 to the negative 3, then divides. I'll put my bracket on 0.032 square multiplies 0.012. Good. So that gives you a thing 332.0. Yeah, you can put 0.01, 0.03. That's it. Now, when we talk about the units, let me come to my yellow. I'll use this guy. When it comes to the unit, what's the unit for? Or the units for rate is moles per dm cube per second. All right. Divides. Now, this square is moles per dm cube multiplies moles per dm cube multiplies again what? Moles for this one per dm cube. So moles strikes mole, dm cube strikes dm cube, leaving mole square, that's per mole square. Right. So you have dm cube 6. It's dm cube 6, please. It's not 9. You add the powers. Remember lots of indices. You add the powers per mole. Okay. Per mole square. Remember there are 2 what? Moles there. And finally your per second. That's it. So that's a unit. That's a unit there. Thank you for that. Now, before we round up, I want us to remember method 2 for your experiment 4. Experiment 4, I will go to this. Now, for your method 2, you just need to use now the rate constant. So using the rate constant, for example, your rate will be equal to 332 concentration of what? Now, what's the concentration of nitrogen monoxide in experiment 4, 0.096 and 0.036 for oxygen. So 0.096 square, 0.036. Use your calculator. 332 multiplies 0.096 square multiply 0.036, and that gives you the same answer, 0.11. All right, so that is that about that question. We've used two ways to calculate one of the initial rates, and we've also looked at how to determine the order of a reaction from your table, from your data or values of concentrations and your initial rates of reaction.